In C, and many other languages, the details of how the compiler codes the evaluation of conditions gives us a trick to stopping sentinel-controlled loops that are looking through a data set. This truth table shows us the definitions of the and or operators. For example, if A is true and B is false, then A and B is false, but A or B is true. There's something really important to notice here. Sometimes just knowing the value of A is enough for us to know the final result. For example, every time A is false, A and B is false. Once A is false, there's no way B's value can affect the result. Similarly, if A is true, then A or B is always true. The compiler takes advantage of this detail. If the first operand's value tells us the final result, it doesn't bother to evaluate the second operand. This is called shortcutting the evaluation. To see why that matters, let's look at an example. This is a sentinel-controlled loop that is walking through an array, and it will stop when it sees the first negative number. Let's be the machine to see how it works. We start by declaring I and giving it a value of 0. Then the loop checks what's in x sub 0. That's 42, which is greater than 0, so we do what's in the loop. That I++ is an increment operator, so the value of I will get bigger by 1. So now it's 1. We go back to the top of the loop. Since I is 1, we are now looking at x sub 1. That is negative 14, which is not greater than or equal to 0. So the condition is false, and the loop ends. See? We stopped at the first negative number. Let's think about what happens when there are no negative numbers in our array. The first time through the loop, it will compare 42 to 0. Then it will compare 14 to 0. Then it will compare 19 to 0. But then what will happen? Well, C doesn't know the length of the array, so it'll just keep going. It'll look through the next position of memory to see if it's negative, and if not, it'll keep going. So this loop could run through your memory well beyond the end of our array, searching for things that look like negative numbers. That is not good. So we need some way to know where our array ends. There are two ways of doing that. The first is to have a separate variable that holds the number of positions in our array. Anytime you pass the array around, we have to pass that int around with it. When we learn about structs, we could package them into one thing, but for now, we have to pass them individually. The second way of knowing where a loop ends is to make it one position bigger than it needs to be, and putting a special value that could never exist in the data we're storing to mark the end of the array. In this example, I need my array to hold 42 things, so I make it 43 positions long. Then I put the largest int possible into the last position. Now for that to work, I need to be really sure that I would never store that value anywhere else in the array, because seeing that value tells me that the array has ended. Now, let's go back to that loop that was searching for the first negative number in the array. Remember the problem we had? If there were no negative numbers, it would wander off the end of the array into the rest of memory. We need to make sure that the comparison doesn't happen if we're beyond the end of the array. If we keep track of the end of the array by storing its length in a separate integer, we can fix things this way. Notice that we are checking to see if I is a valid index before we use it to index x. Since the compiler shortcuts the evaluation of the and, once it sees that I is equal to x size, it knows the and will be false, so it doesn't do the second comparison. Similarly, if we track the end of the array by storing a flag right after the last position, we can compare x sub I to that flag. If we've hit it, the first operand of the and will be false, and the compiler will know to stop the loop. These extra terms in our condition are called guard conditions, and they help us stop the loop before we wander off the end of the array. Notice that shortcutting the evaluation of and or means that they are no longer commutative. The order of the operands matters. If we put them in the other order, then we will index the array past where it ends. In this case, in C, that probably doesn't matter because we're just looking at the word in memory. We aren't changing it. However, it's bad form to reference memory incorrectly, and in other languages that will break things. So we always put the guard condition first. Bottom line, the order of the operands around and or matters. The machine will evaluate the first one, the left-hand operand, and if it can use that to make a conclusion about the value of the and or, it will stop there and never evaluate the right-hand operand. We can use this to build guard conditions to prevent invalid memory accesses.